This is Dr. Wood with Citadel Civil Engineering. This is CIVL203 Dynamics. And in this lecture, we're going to talk about learning objective 3.4, or the idea that I like to call kinematic triage. So when we think about this, what we're really doing is we're going to wrap up and bundle together all of our particle kinematic knowledge that we've developed to date. So we're bringing together the equations of motion that we learned about in chapter 12. We're bringing together the work energy concepts we learned about in chapter 13.1 and 2, as well as the impulse, momentum, and impact concepts of 13.3 and 13.4 from your textbook. And when we look at those, we realize we've got all these different tools, but remember, they're all basically related to the equations of motion and Newton's second law. In some cases, we've blended the kinematic relationships into it to make them easier to work particular types of problems. And so what we want to do now is we want to talk about how we make the choice about which tool to grab. And so when we think about kinematic triage, we're thinking through, do I want to try and approach a problem using the equations of motion? Do I want to try and solve a problem using work energy? Or do I want to try and solve a problem using impulse, momentum, or impact? Kind of impact as the special case of impulse momentum. So we kind of want to know what to think about these different things. And so if we look at this figure from the textbook, this gives us a great ability to kind of compare where we might use these things. When we think of the equations of motion, we're using the sum of the forces is equal to the mass times acceleration. So Newton's second law, simplified for when mass is constant. This is going to be our go-to. We're going to draw a kinematic or a free body diagram to do the sum of the forces, and then a kinetic diagram to look at the mass times acceleration. So I'm going to fill out all these notes here, and then we'll look at that diagram there. So this works best when we have a single moment and we're thinking about forces and accelerations directly. Because if we don't have acceleration, we're going to have to use our particle kinematics to identify the acceleration at those single moments so that we can use this equation, the equations of motion, to come up with the solution. And so that's a great way to work, and it's super powerful, and in some cases it'll be the only solution that will give us the data we want to know. For example, normal forces are best calculated using the equations of motion. Our work energy equation says that the sum of the work moving from point 1 to point 2 is equal to the change in kinetic energy. And so we'll remember that when we talked about work, that's force times displacement, and kinetic energy is based on the velocity of the object. And this is great for when we're looking at two positions, or the change between two positions. And we've been told or asked for something where we have force, where we have displacement, and where we have velocity. So delta S or R, delta R, and our velocity, or specifically our speed, because we don't actually care all that much about the direction of the velocity because we square it, 1/2 mv squared, right? And it's the scalar term, we can solve for one unknown. And so this is great when we're seeing these changes in positions. And what it means is that we're not actually ever going to calculate the acceleration directly, although once we have the velocity and the position information, we certainly could use our kinematic relationships to go solve for the acceleration. But if we're interested in acceleration, we might try to use equations of motion directly. Finally, impulse and momentum, where we said that the sum of the impulse, which is force times time, is equal to the change in the linear momentum. This is going to be best for when we have collisions or short duration interactions. So we have kind of a before and after view of what's happening. And or when we've been told about the force, the velocity, in this case it would be a vector, and the change in time. So here we're looking at position and velocity. Here we're looking at time and velocity. And so we want to be able to pick the appropriate tool for the appropriate portion of the problem. And so if we look at this diagram from your textbook, we can see that if we're moving from one point to another with a significant change in displacement, what tool do we want? It's a change in displacement. Well, displacement should immediately cause us to think about work energy. So we'd be looking at the weight, right? Now, if we wanted to know the force on that string, remember that force is normal to the path, so it's going to be a lazy force. It won't show up in the work energy. We would have to look at a particular moment and use our equations of motion. And so in this case, it'd be easy for us to use our path. So you start with work energy, solve for the velocity, and then we could use path kinematics to be able to say that the normal acceleration is equal to v squared over rho. Once we have that acceleration, now we can solve for the forces using the equations of motion. So that's a valid way to do that as well. When we look here, we see a very brief duration in which we have a lot of impact going on. So we can look at impulse momentum, or if we don't actually care about what's happening during the impact, we can look at impact itself and the coefficient of restitution and the conservation of momentum to solve from that initial condition to the final condition. And so we can use impact because we have something of very short duration. And then if we're looking for the conservation of, or if we're looking at the final position, again, that brings us back to work energy as we go along. And so I hope you see here that we have the ability to use all these tools. And often what's going to happen is that you're going to be working on a problem in the real world or on your homework, and it's going to take using and being able to grab these tools to do the different things we need to do to solve the problem. Very rarely is it going to be just like, here's a screwdriver, there's a screw, we only need one tool and it's done. Now, to ease your mind on exams, I do like that type of problem that's very much one and done, like pick one tool, solve the problem, be done. But on the homeworks and in your projects, and as you go forward, when you use these concepts, it's not always going to be immediately clear which tool is the best tool. And so we want to learn to be able to triage, to prioritize which tool we'd want to start with. And so if we're looking at a single moment, the equations of motion. If we're looking at a change in position, work energy, and if we're looking at a change in time or something very short duration, impulse, momentum, and impact would be our tool. All right, I look forward to working some more complicated problems with you in class. Take care, and I'll see you then.